We hope you're enjoying the day so far. The next session will be all about storage. Phil Williams, who is responsible for Ceph and other storage solutions at Canonical, will introduce you to the versatility of Ceph. Phil has over 18 years of experience in the storage industry, having previously been responsible for storage and infrastructure products at a number of leading technology companies. In this session, you'll see how to set up a demo environment that you can run on your own laptop to explore Ceph as a scalable storage solution for AI. Phil, the floor is yours.
Hi everyone, welcome to this session. Let's get started learning more about Ceph and how it can serve the needs of AI applications. So for those of you who are yet to hear about Ceph, experience it, let's start with a brief overview. Ceph is a storage solution designed to meet all storage needs, from a few gigabytes to petabytes, all the way out to exabytes. It can provide block, file, and object storage from a single cluster. Hardware can be chosen with price performance needs in mind, balancing performance and capacity with underlying hardware costs. Canonical Ceph provides high levels of automation to drive down the TCO, or the total cost of operations, of the entire storage system. So what are the benefits of Ceph? The underlying architecture of a Ceph cluster allows a user to start with something that's relatively small, and over time add additional nodes to grow and scale out in line with their needs. Ceph is super reliable. In fact, the cluster's number one goal is to ensure that data is always protected. Even during hardware failures, when you're growing the cluster, when you're shrinking it, that's its primary purpose, is to protect that important asset that you've stored in there. Ceph is very flexible. We can create a single cluster that serves multiple needs, as I mentioned. For example, we have some data that we must keep. We don't access it very often, so alongside maybe like a general purpose storage pool that has a mid-range performance characteristic, we can create another pool that's more aligned to an archival use case, with very dense drives and no flash-based cache, just super simple, super dense storage for an archival use case. We can automatically upgrade the Ceph cluster between different releases of Ceph without interruption. This is obviously super important in the world of non-stop operations. Security is, again, highly critical these days. The great thing with Ceph, we can deploy it with the underlying disks being encrypted, so that if a drive does fail, you can take it out of the system, you can return it under its warranty, and there's no risk of exposing any data that theoretically could be retrieved from that piece of hardware. So it removes a huge amount of risk and a huge amount of administration sort of overhead. Ceph can also provide super cost-effective solutions, as partially from reducing the amount of capex that you spend by utilizing off-the-shelf hardware, but also reduce the operational expenditure because it's self-monitoring, it's self-managing. A drive fails, you don't have to immediately worry about it. You can, we have customers today who treat drive failures in like a batch. They'll have a drive fail, they'll just leave it in the system, and maybe once a week or once every few weeks, once there's been several drives failed, they'll go off and they'll replace all those drives at the same time. So what does a Ceph cluster actually look like? So let's take a walk through this architecture. This is a multi-protocol Ceph cluster, provides block, file, and object storage. And there's some mandatory components in there that you have to even have a Ceph cluster, and then there's some optional pieces. So let's start with the mandatory pieces. So Mons, managers, and OSDs. The Mons, they are the manager of the cluster, the orchestrator, if you will. They also maintain a map of where things are in the cluster, the state of the cluster, things that are going on, during hardware failures, or when a new client accesses, those kinds of things. So they have a map, what we call it the crush map, and that gets updated every time like a disk is added, a node is added, something fails and is removed from the cluster. And when those events happen, they will trigger resync events to make sure that data is always protected. And also the Mon's job is to handle authentication. So any time a client accesses the cluster through any of the possible entry points, the Mons are the things that provide the underlying auth system into the storage system. Managers are responsible for tracking performance metrics of the cluster. and they expose that performance data for consumption by other solutions like Canonical's observability stack. At the end of the day, it's a Prometheus endpoint, so you can scrape it with any tool that you so wish. Bottom of the slide, we have some OSD nodes. So these are the storage servers that actually contain SSDs and hard drives. They hold a user's data. I've represented them here into 3 different stacks across the slide, and that typically represents how we see customers deploy this across different availability zones. So if you think of a 3 replica kind of configuration, each availability zone has 1 replica of data. If you think of an availability zone as like a different cabinet or a different power zone in your data center, one piece fails, the other 2 still remain operational, and data is still available. The system's still available for use. Block clients, they interact directly with the OSDs, so they speak to them on, they get the map, they get authenticated, and then they can access the OSDs directly. And this gives great performance because they're able to access all of the underlying disks or OSDs across the entire cluster. It's a great way of scaling performance across an individual volume. For object clients, they communicate with the cluster via the Rados gateway. And so the Rados gateway is an extra daemon, and it runs a HTTP endpoint, which is S3 and Swift API compatible. For network file system access, that's using Cephfs, so Ceph's native networked file system protocol. And in situations where we need to use Cephfs, we also deploy an extra daemon called the MDS, the metadata server. And again, this acts as a map, or how to go and find the individual objects of data that are stored within the back end of the Ceph cluster. We also have an iSCSI gateway. It's not highly used. iSCSI is what feels a bit like a legacy protocol these days. But in the coming few months, we will also be adding support for NVMe over Fabrics. So that provides an industry standard blocked or a network block protocol access into this open source storage system. So with Ceph's ability to use off-the-shelf hardware, we can kind of tweak and tune the choices, when you come to build one of these clusters to meet all these different competing needs of what I like to think is storage economics. So it's this fun balance of, what does an application need in terms of performance? How much data does the application need to store? How much is it going to grow over time? Seems to be a very common pattern. Reliability, what kind of reliability does the system need? Do you need to have 3 replicas of data? Do you need 4? Do you want to use erasure coding so you get better raw storage usage or efficiency? You kind of have to balance all these things together to kind of fit with the final point here of cost. At the end of the day, any kind of storage system costs money, any kind of infrastructure costs money. So we always have to take into consideration, do I make the fastest possible system for an application that does really need it? Am I providing enough capacity for the application that needs to run on there? If I don't have the capacity, the application is eventually going to fill it up and it's going to fail. And then balancing the reliability side of things as well. So it's a very pragmatic kind of decision that you have to make when designing a storage system. But that's the great thing about Ceph. We can kind of pick and choose. Can balance different pieces of hardware, different CPU types, amounts of RAM, networking choices and configurations, just to balance across all these different areas. So this is typically where you see 2 types of storage architectures. So firstly, there's scale up. It's a fairly typical model in a proprietary system. You start with a head node, and then over time you add more shelves of disks, and more shelves of disks, and more shelves of disks, and more shelves of disks, until you've basically filled up all of the potential slots within that storage system. You've reached the maximum capacity, and then what do you do next? Your next choice is to actually go off and buy another storage system, and then you have to manage two different essentially silos of capacity. And the other challenge here is that you're still relying on that like same head unit or controller unit. So that means that your performance is always going to be limited by that particular component. Adding drives gives you more like drive performance, but if you can't get that through the head unit, then you're always going to be bottlenecked there. So in the second scenario here, and this applies to Ceph, is that you have this idea of a scale out system. So every time you add a new component or new capacity into the cluster, you're also adding CPU, RAM, network capabilities, as well as the disks. And that leads to an almost linear performance improvement as the system grows and removes that kind of bottlenecking that you see with a scale-up system. So now we understand how Ceph scales out, some ideas around how you how the cluster looks, and how you can kind of choose some of the hardware that goes into it and the kind of resources that go into it. Let's start to tie some of that scaling goodness into a growing AI infrastructure and how the two kind of fit together. So firstly, let's briefly touch on some of the types of data that you need to you might run into in the average AI system. So kind of self-explanatory raw data. It can be all sorts of unstructured content. This is great. This is great use of object storage, actually. It can be stuff like video, audio, text, email, chats, telemetry, all that kind of like almost what I call like tick data from autonomous vehicles or IoT devices, that kind of like high volume needs to be processed kind of data. Training data. So this is a more organized, structured data set, which can be used for things like pattern matching. So imagine you're training a model to recognize number plates, license plates from cars. It's essentially examples of that to give the training system an idea of kind of what to look for in a future model. The important thing with some of the training data is it's actually really good to preserve that exact data set so that you can then go back in the future to reevaluate and model against the same like set of data. If you use a different set of data with the model, it would be kind of difficult to yield like a fair test or a fair comparison. Obviously, once they're created, a model is very important to keep a hold of. It takes a lot of GPU time to actually be able to build a model. Sometimes it can be weeks, months. So preserving them once they're created is super important. And then finally, after what it feels like, a lot of steps and kind of get there, the results from all this, you run a data set through a model, you've got a bunch of results. You do need to keep hold of those as well. And then you can actually use them to, make decisions or, choices from the data that you've been able to process through your AI system. These data sets can be stored in a mixture of like block, file, object. And again, this is another great reason to use something like Ceph, because of course we can provide all of those different storage endpoints from that one same system. You don't have to manage them independently. So what makes AI storage needs so special? Let's take a look at something like NVIDIA's H100. So from a computer perspective, a single card can peak at about 4 petaflops. So for us storage folks, what does that really mean? Well, it means that we need to provide it with about 5 gigabytes per second of data to keep it fully utilized. Let's scale up a little bit. So this is a DGX H100 system, contains 8 of those GPUs. So now we need to be able to provide 40 gigabytes a second to keep this system highly utilized. Fundamentally, the individual GPUs don't change. It could be this. Okay, this is NVIDIA's sort of example, but it could be a system from any of the other OEMs as well. They're all the GPUs are still hungry. And then we take this quite a leap further. So we go to a large scale cluster configuration. So something like NVIDIA's SuperPod approach. So that's, as a start, 32 GGXs with 8 GPUs each. So that's 256 total. That then means we need to be able to provide a peak read bandwidth of around 1 terabyte per second. to keep the system highly utilized. Of course, in these nodes, there is local storage available. So some of the operations where data is reread multiple times can use that as a read cache in front of the external storage cluster. So that certainly helps. But that initial kind of like read, and then some of the checkpointing operations where we would have to do quite significant writes to the cluster, we're looking at, new and very significant increases in performance and in kind of scale. So being able to combine this idea of scaling out both performance and capacity by adding more nodes and more resources into a cluster really does help get that new level of storage throughput into an AI system. And the great thing about Ceph again is that adding additional nodes like that, it is an almost linear increase in performance as you do add those nodes. So Ceph kind of sounds quite cool. How can I try it out? So we created this thing called MicroCeph. It's kind of Ceph for non-experts, users who need either reliable deployments in all kinds of different environments, from dev, CI, edge use cases, large-scale production. The idea is that deployments become a few commands and data ops like scaling are really like simplified. So MicroCeph, despite its name, retains all of the goodness of Ceph. The idea that micro is not to do with size; it's more around micro operations. It's all about making an administrator's life super easy. MicroCeph is delivered as a snap, so all of its dependencies are packaged together, and it runs fully isolated from the underlying host. And we'll look at that in a little while in a demonstration. By using channels, we deliver multiple different versions of Ceph as well. So right now we have stable releases for Pacific and Reef, and under the Edge channel, we also have a Squid release as well as we get close to the GA of upstream Squid. So to get started, it really is just 3 commands, and you can get a minimal Ceph cluster up and running. And this will give you a block storage endpoint, be a 4th command to add the Rados gateway endpoint, so you could start using S3. We'll see that in the demo. So what happens here is we install the snap. During the bootstrap, we basically create an individual mon. In this case, it will be a single node, and that brings the cluster to life. And then we can add a bunch of disks. What we're doing here in this sort of quick example is using what we call a loop file. So that's basically just like a mock disk, perfect for demonstration kind of purposes, perfect for CI as well. Obviously, in a real world deployment, we would use a physical disk. So coming up in the demo, what we're going to do is do that installation, do the bootstrap. We'll add a disk, just one, and some caveats around that. We'll enable the Rados gateway with the S3 endpoint and configure it. And then we will actually make use of the gateway and just interact with the API. And then, of course, we'll clean up after the demo too. All right, so here we're just going to install the MicroCeph snap. And we're going to use the Edge channel. The reason for doing that is that it's quite nice to be able to test out these kind of latest versions of Ceph. So this is a preview of Squid that's due for release anytime now. And now we're going to bootstrap the cluster. So as I mentioned, this is going to create a mon. It's going to get the cluster set up and get things kind of ready and running for us. Now we'll take a look at the cluster status. So health is okay. We have 1 mon daemon. We don't have any OSDs yet, but we do also have a manager. So we could actually start looking at some of the performance metrics coming from the cluster. So let's add a disk. And like I said, we'll use a loop device. Just a few gigabytes for this test is plenty. And we should get a successful return. There we go. And now let's take a look at the cluster status. So we do see a warning, but again, it's because there is only one OSD at this point. This is just quick kind of demonstration and exploration of what you can do just on a local machine. There we go. We can see in the OSD tree as well. So what we need to do now is so that we can make use of this single OSD Ceph cluster. We just need to let it know that it is okay to have a pool with only one one replica and one device in it. This is not something you would do in production. It's purely for kind of demonstration and kind of dev purposes when you try this system out. So now let's enable the Rados gateway. And what this is going to do is create a Rados gateway daemon, create a number of pools on that single OSD so that you have all the metadata and things like that for Rados gateway. A Rados gateway daemon is kind of stateless. It doesn't hold anything in the daemon itself. It's all stored within the underlying Ceph cluster. So there you go. You can see we now have 5 pools in the storage system. Bunch of objects there as well. Again, it's the metadata. So now we need to set up a user so that we can interact with the S3 API. So what we'll do here is just create a user with the name dev. And the display name will also be dev. Keep it quick and simple. So that's our user created. What we should do now is copy and paste the access key and the secret key, because that'll become particularly useful in a second when we install and configure S3 command as part of the demo. And it saves memorizing those quite lengthy strings. So let's just quickly install S3 command. And now we need to just create this configuration file. So there's a nice walkthrough step here. So we can paste in that access key that we just created as part of the dev user, and also the secret key. We can ignore the default region. We can set the endpoint just to be in the local machine's local IP. We also just need to put in a kind of dummy DNS record here so that S3 command doesn't get confused when it doesn't actually interact with the S3 endpoints. We're going to use encryption, so we can skip that. It's important in this kind of scenario to disable HTTPS. It's just local, so there's no benefit of using it. And you can see there that we just got a quick test operation, and we can see a confirmation that worked fine. So we'll save that file. And then now we can start interacting with the endpoint. So first, let's create a bucket. So I'm just going to create this bucket called test. And let's see if there's anything in that bucket. Of course, it's brand new, so it should be empty, but let's just confirm that. And then that means we can also verify when we do upload some files, what has actually happened. So on this machine, I've got a few JPEGs, which we can upload to the S3 API with this put command. And it'll go into the test bucket. And there you go. You can see that file has been pushed into the bucket. Now let's do the list again, and we can confirm that file is now existing in the object storage system. Of course, cats get lonely, so let's give them some friends and add a few more files as well. So we've added cat2 and cat3 as well to the bucket, and there you go. Listing it again, we can see all of the files within the bucket. So while this is a really simple example with that access key and secret key, you can put that into an application that you're developing, any kind of other data science tools that need to interact with object storage, and you can use the object storage in the the same way as you would in the future when you do a production deployment. So here, as we just clean up after ourselves, the great thing about it being a snap, it's one command and everything is removed from the system that you've been using for this quick sort of tryout of Ceph. So the demo is cool, and it's a great way to see how you can get started with Ceph. You can try it on a local machine, a VM. If you don't have a machine that has Snap natively, you could use something like Multipass to create an Ubuntu VM and then do the same kind of stuff within that sandbox environment as well. But if you want to go and think about data center scale, how can you leverage MicroCeph? And so the thing that allows you to do that is Charm MicroCeph, and this is where Juju and Charms kind of come into the picture. So for those of you that are not familiar with Juju, Juju allows you to deploy any application at any scale on any platform or substrate. So in this situation, we really care more about bare metal, but it does support other things like K8s, OpenStack, AWS, GCP, Azure, all the public cloud, well, a bunch of the public clouds, and you can even use a VMware backend as well. You can use the same charm across multiple substrates, so you have very portable kind of operations with your applications across those different substrates. And it means also that you only ever learn kind of one set of tools, but can still leverage all of those different platforms if you should wish. So what is a charm? A charm takes domain knowledge and expertise, so like that kind of operational behavior that a sysadmin would have, and it programmatically represents a way to effectively operate software. So in this case, we're talking about Ceph. So the MicroCeph charm, so to combine the cleanliness of Ceph delivered in a snap with kind of those larger scale operational needs, we created the MicroCeph charm, and it allows you to use Juju to deploy and manage a Ceph cluster, truly at data center scale. There's no hand cranking involved like there was in the demonstration, and it allows you to then integrate block, file, and object storage with a bunch of different applications absolutely seamlessly. So we have integrations into OpenStack, into Kubernetes. We use traffic for load balancing the endpoints of Ceph as well. And then kind of finally, what the MicroCeph charm brings also is a real orchestrated way of being able to do cluster upgrades, help with actual hardware management. So adding OSDs, removing OSDs, kind of pool management, dealing with the components of the Ceph cluster as well. So it does provide this true overarching operational experience of a super robust and super kind of complicated distributed system underneath it. So with that, I hope this, what feels like a quick overview and quick demo, provides a taste of how Ceph scale out nature does actually fit with these very large scale AI deployments that are occurring across the industry. And honestly, even if your AI journey is not kind of underway, these concepts around the storage system and its scaling out can also apply to many of the data center workloads. So that it's not AI specific by any means. It's one area where we see lots of growth and lots of demand for high performance storage, but also it still applies to any other storage workload in your enterprise. So if you want to find out more about Ceph and how it can help you with your storage needs, please visit ubuntu.com/Ceph. All the product information is there, all the documentation to get you started is there, and you can also get in touch from that page. And with that, thank you very much. I hope the session was useful.